Okay, so we're going to get a very, very general high-level overview of support vector machines. There's going to be a lot of stuff in these lecture slides, but what I really want to drill down is the concepts here.
Okay.
Here's a funny joke.
Wait, wait, I haven't looked at it.
This
7
is
times 0
dumb.
equals 0, 3 times 0 equals 0, 0 equals 0.
Oh, okay.
This is stupid.
Is that Neil deGrasse Tyson?
Yeah, we'll come back to this. Okay, so we're going to motivate support vector machines by talking about linear classifiers and perceptrons. Were perceptrons in the reading?
He mentioned it like just very briefly, like as an example or something.
Yeah, because I read. Okay, I didn't think they were. So we'll start here. We'll talk about support vector machines and parameter learning. We'll get there. So basically, given some training data, I forgot this is the one that's already. Here we go. Let's start here. Okay. So given some training data, x of i's with labels y of I for I equals 1 to n, right, we have some data that has d dimensions with labels -1 and 1, and we want some classifier f of x such that, if you throw your data x of I in there, and if the output is greater than 0, then you're going to label it +1, right? And then if the output is less than 0, you label it -1. Right? This is just a binary classification. And so we want to basically have it such that the classifier times whatever our output is going to be greater than 0 for a correct classification, right? Because if you had a negative, if you classified it as -1, right, as a label, -1 times -1 is greater than 0. So no matter what, +1 or -1, it's going to be greater than 0. And we look at these two different data sets, right, where it's very clear to us that there are two different types. We have blue circles, we have red triangles, and we want to be able to classify these in this scenario and in this scenario. Well, they're a little different. And so one of the ways we can describe, I guess, these classified data is if they're linear separable or not. So here's a really easy example. This is just right here, where we have a linear separable data set. We can just draw a straight line. It completely classifies our blues from our reds, right? And even in this situation where it's not as obvious here, but you can still draw a linear line that separates our data set. Whereas in this case, once we throw one of those reds over into the blue section, even if I draw this line here, I didn't separate out my data set completely. So this is an example of it not being linear separable because, we have some error here. Another example is this where, in order to properly classify, I'd have to do something like draw a circle, right? And that's not linear. It's not a straight line. So this is another example of not being linearly separable. Any questions here? Okay. So when we're coming up with our linear classifier, it's going to have the form f of x is equal to x times theta plus theta naught, where theta is normal to the line. So we have some line here. Theta is this vector, and it's going to be the vector is going to be normal to this line that we draw here, where f of x equals 0, right? And depending on your x point that you throw into your classifier is either going to be less than 0 or greater than 0. Right, that's how we know, how to classify it. And then we have this theta naught, which is the bias. The bias essentially moves this left or right in this scenario. It's just a constant term. And theta is going to be known as the weight vector. So in the 2D scenario where we have two dimensions, x of 1, x of 2, that describe our data set, then our linear classifier is a straight line. It's pretty easy to see. But now, when we move to higher dimensional, so in this case, we have 3 dimensions, So now we have x of 1, x of 2, x of 3. Here's our data set. We can still use a linear classifier, even though it's greater than 2 dimensions, and it still has the same form. But now f of x, where f of x equals 0 used to be a straight line, now it's this, in this scenario, it's a 2D plane, but more generally, it's going to be a hyperplane. So it's going to be some hyperplane, basically some kind of surface relative to whatever dimensional data set we have, that's going to cut through our data set in a way where if f of x is greater than 0, it is one label, less than 0, it's another label. And then where f of x equals 0 is what we call the decision boundary. So that's just the high-level overview of what a linear classifier is. So now we're going to move on to this idea of the perceptron classifier. Given a linearly separable data set with labels of -1 and 1, we're going to find some perceptron classifier f of x of I equals x of I times theta, where it's just like this form, but now we've thrown this theta naught into our vector theta, where so the bias is internalized in that vector, right? Whereas before it wasn't. And what we're doing is the perceptron is going to separate labels 1 and -1 using a line, but we're going to find this line with an algorithm, right? So this is just like let me actually start here. So basically what it does is it's going to start with the bias equaling, not the bias, but the weight vector equaling 0. We're going to go through each data point, and what it's going to do is it's going to predict and then learn as it predicts. It's going to like get better. So it's going to initially say, okay, I guess my bias is going to be 0. I'm going to try and label and with each data point, and if I fuck up, if I get it wrong, then what I'm going to do is I'm going to adjust my bias by this formula here. We're basically using some hyperparameter y of 1 times x of 1. I'm going to push my original bias guess to some new bias guess. And I'm going to do that until all the data points are classified. So I start at 0, I go through all the data points, and then I end up with some line. Does that make sense?
Mm-hmm.
Right, and so you're learning as you predict until you've gone through all the data points. So again, here's the algorithm. We start at 0, we go through each data point, we correct ourselves until all data points are correctly classified. So let's say we start here. We're at this point, we have our reds here, our blues here, we have this red here, right? And we can describe x of I as this data point for this red. And now what we're going to do is we're going to apply our perceptron. Okay, it labeled this as blue, right? This is on the other side of the line. So this is wrong. And now what it's going to do is it's going to use this formula to update. So now it's pushing this over, right? So we've updated it to account for this. And now here's our new bias term after it's been corrected using the perceptron algorithm. And then you can imagine that, right, it might do another update where maybe it focuses on, let's say, this one. And, you know, it's going to get that, it's going to label it red, that's wrong. So now it's going to update, and it might end up drawing it like, ooh, can I undo that? Here we go. It might update again, draw something like that, right? And then you'd have a perceptron that accurately classifies. Does that make sense?
Mm-hmm.
So over each data point, it updates itself, reclassifies, tries to do better. So let's see. So the order is kind of weird here, but as an aside, you know, just because we've drawn a line to classify doesn't mean it's the best it can be. So here's an example of different separating lines, right? In all these scenarios, they're like good classifiers because we have the reds here, we have the blues. I don't know if it's blue or black. Black? I don't have enough cones in my eyes to tell. So we draw our line here, right? This is accurate, this is accurate, this is accurate. But if you had to guess, and this is where I'm going to ask for your input. Which one would you choose? Which one's best?
Probably the one with the best, with the last one, the one on the right.
Yeah.
Why?
Because if you have a bigger error bound, if you have a greater tolerance for error, then your line will be more likely to be more separable. Like the data points will be on the outsides of those error margins.
Right. So this is our margin, and it's not quite error. This is one way you can think of it is our functional. No, this is actually our geometric margin. But
I meant to say I use the word error margin, but I meant more like tolerance.
right. So we can use that term. So right here, right, this is so close to this data point that let's say that we had a bunch of new other data points. The odds of it being misclassified are higher because look how close it is to this, right?
Right.
So we want to maximize the margin between the minimum. I guess we want to maximize the minimum margin as much as possible, right? So here's like the smallest margin, right? The margin for this line to this is much bigger, but this is the minimum part, right? We
Yeah.
want that to be as big as possible, and that's because as we populate this with new data points, we believe that that's going to be a more accurate classifier than like this one.
Mm-hmm.
You can think about that in terms of functional margin. So basically, functional margin is the confidence we have that this point is properly classified, and that's actually a little above my understanding. But essentially, we want to find the bias. Not the bias, but the the line that is going to maximize the margin as much as possible. So here's another example of this. This is a bad line because it doesn't classify properly. All right, here's another line where like it actually it gets the job done, but look how close it is to this blue.
Right.
Similarly, here's another example. Like these all you could have something, you could define some classifier f of x where that works, and these are both valid, but you really want this one because this is where it's the best relative to these other two options.
Mm-hmm.
So the maximum margin solution is the most stable under perturbations of the inputs. So if you give new inputs, right? If I were to draw, right, where do I do the color? Blue. All right, so if I were to draw like some blue here, right, in this scenario, I'm probably still going to classify it, right? Well, maybe draw some blue here, right? Even though it's still on the side, this might misclassify.
Right.
This will misclassify, but this one won't. This is a better classifier.
Mm-hmm.
Okay.
Makes sense.
So this is now, so with that understanding of how to evaluate classifiers in terms of their goodness, we can look back at the perceptron algorithm where we loop over every single data point, and we learn until we get to some final value where it converges, right? It converges as long as it's linear separable. It's going to get you an answer. It's going to take a long time. You have to go over all the data points, right? So you can imagine the big O notation for something that has a lot of data points. And it's going to end up close to the data, right? You've adjusted it a tiny increment each time until you've reached this point, but like this isn't necessarily the best one. So we would prefer something that is a little more generalizable so you can have a larger margin. That way your classifier is going to be better when you're having new input data.
Mm-hmm.
So this is one of the downsides of using something like the perceptron algorithm. And what this does is this motivates the usage of support vector machines. Okay. So
I think I have read about this actually.
yeah, I think you probably have because you will have learned about it in your convex optimization class.
Yeah.
It's going to use some real mathematician stuff in order to get this job done. And so you'll be familiar with it, I think, in like 5 slides. Hey, Kevin.
Hey.
Okay, so let's begin to talk about support vector machines. So here we are again with our decision boundary x times this theta, And let x of I be the nearest data point to the line. So it can be this one or this one. And we're going to say the absolute distance is greater than 0. All that means is that it's not on the line. If it was 0, it's on the line. So it has to be greater than 0.
Right.
X of theta equals 0. Here's one question. It's not theoretical. I want y'all to answer it. Does it matter if I scale up or down theta for decision boundary? So let's say I took my theta and I multiplied it by 100. Does that matter?
Yes.
How?
Because if you, well, theta represents the, basically what you're going to multiply xi by, right? So if you scale theta, then you're basically moving that point, right?
But also, don't you internalize the biases into theta? So if you're scaling up theta, you're also scaling your bias factor. So wouldn't that make it off?
I think for now, assume that I don't exactly remember how the bias works, but turns out if you were to scale it, you don't really change the decision boundary. Like if you scale this, I guess the way it works is you might change the you might change the total, you want to change the value you get. So when we're
right. That makes sense.
Theta, you change the actual value, but it's not going to classify any different, right? So even though you change the values, you could get you could arbitrarily inflate the values you get, but at the end of the day, it's either going to be greater than 0 or less than 0, and that doesn't change.
Right. It changes the points, but it doesn't change the boundary itself.
Okay.
So
because they're both scaled on each side.
So it doesn't change the classification.
Got it.
So it's useful for us then to normalize this. So we're going to say that the absolute value of x of I times theta, where x of I is the nearest data point to the line, this one and this one, is equal to 1. Right? We're just going to say that is true for us. And now what we're going to do is we're going to change our notation again. We're going to pull out the bias into this b term. So our decision boundary looks like x of theta plus b, y equals mx plus b, right? This is a linear line. Okay, we'll come back to this normalization idea. Okay, so now what this slide is trying to do is motivate the formula for computing the distance. So let's say the distance between x of I and the line, we want to find the distance between x of I and this line, where x of I theta plus b equals 1, the absolute value, right? Because that's just what we said, right? We said that here. And so before we do that, let's consider some arbitrary example, x prime and x double prime that both lie on the plane, our decision boundary plane. And that means that x prime theta plus b equals 0, because it's right, this line is where f of x equals 0. Same thing for x double prime. We're going to do some algebra, and we can see that if you just multiply these values times theta, it has to equal 0. So right now we're just doing some arbitrary example. We're going to get back to calculating the distance x of I. Okay, so now we're actually going to try and calculate the distance. So what's the distance between x of I and the plane? Let's take any point x, so that's on the line, so some point x, and the distance will be the projection of x of I, of this distance, x of I minus x vector, on theta. So we're going to basically project x of I onto this line and then compute that distance. So to project the vector, well, I think we're going to project the vector, we want to project a vector onto this line. I'm just not sure which vector. So if y'all see that, let me know. But basically the idea is that in order to project, we're going to need to normalize. So we're going to say that this normalized vector that allows us to project is going to be this vector here divided by the L2 norm. to get the, and then given that, we can say that this distance is going to be this times the projection, which is this unit vector here. And rearranging, so we say we replace this with this term, and then we'll pull out this, and we multiply this through, we end up with this. So we're saying that our distance between, for x of I and x, some arbitrary x, is equal to this. We're going to add the bias back in. So we pull out the bias just so we can see that our constraint, where we said that this distance, this must be equal to 1. I'm trying to think where we said that. Yeah, we said that for x of I, where do we do that? Fuck. Yeah, we said that this, we normalize it such that this distance equals 1, right? So this is equal to 1. Any point on the line must be equal to 0. So this simplifies to this. This is our margin, right, between x of I and our decision boundary. So remember, what we're trying to do here is maximize the margin. And the problem here is that, so we can represent it like this, right? We just arbitrarily multiply by 2 because we can scale, it doesn't really matter. And then we're going to minimize this value, x of I theta plus b, or we're going to maximize this such that our constraint is true, where like we normalize this to equal 1. This sucks because it's non-convex. It's really hard to maximize. So we're going to, what the remainder of the few slides are trying to do is fudge it into some kind of form where we can now use an easier way to optimize with convex optimization. So that's what these next few steps are. So we're going to say that if we correctly classify, then this is equal to 1, which is also equal to this, right? This is our label, this is our output. It should equal 1, even if it's negative. Even if it's on either side, it should equal 1. So if the minimization of this equals 1, what we're going to do is we're going to replace this constraint with this inequality constraint. All right, so we're getting there. I'm going to skip some stuff because the math is over my head. And we're going to get to, what I'll say is, I think what Andrew Ng does, the derivations in the lecture notes.
It makes sense, like what they're talking about. Like, so 1 over the, what it looks like the norm, that distance from the decision boundary to the first data point.
Right.
That is what you're maximizing. So that, I mean, you see that where it's maximizing. When we relax the inequality, so you have like y of I, and then parentheses x of I theta plus b has to be greater than 1. That's like all correctly classified values. So you're just trying to make sure that by maximizing, you're just maximizing a decision boundary, given that you're going to at least have all of the correctly classified values above that value. Like, well, you see what I'm saying?
Yeah, I think so. But let me try and explain kind of a little bit what's going on. And I think that might help because you can't just relax the inequality. So what's happening here, I'm not sure exactly what's going on geometrically, why you drew this up here. But basically what they're saying is that, like, you know, you could try and maximize like this, or you can reframe this where the L2 norm is just like the square root of this times like this. And basically what we're going to do is we're going to rewrite this as half of theta times theta transpose, which is like theta squared essentially. We're going to minimize that.
Well, you just inverted that, right? Maximizing that number. If you invert it, then it's minimizing that number.
So they inverted this because, again, we're trying to fudge this into something that we can use convex optimization. And we're really close, but we still have this inequality. So in order to get rid of it, we're going to use, some kind of Lagrangian method where we use the Karush-Kuhn-Tucker condition, and there is some complementary condition here that comes a part of these assumptions, where basically all it's saying is that g of x times alpha, where alpha represents the basically our Lagrangian multipliers, right? Such that whenever, this here's a visual version of that. Whenever g of x equals 0, the Lagrangian must not be 0, right? G of x is, whenever g of x equals 0, the Lagrangian has to be greater than 0. Whenever g of x is greater than 0, here, the Lagrangian must be 0. And because of that, we're able to, once we use that formulation, I guess I'm not exactly sure what the math steps are. This is like some real mathematician stuff. We end up with, where do I stop up? Stop this. Oh my gosh. I think it's here. I think here's the primary optimization problem. And then what we're going to do is we're going to use the dual version of this. Let me see if I got that term right. This is the primal problem. And the solution of this is the same as the dual problem. I think this is the dual problem. Again, this is like math stuff way beyond the scope of what I can properly present to you. But Andrew Ng does go over it in his notes. So essentially, we're going to use quadratic programming packages to solve this. And like we've rearranged from our original formulation. Let's see here, where all we're trying to do is maximize our margin, right? And then through a lot of fancy steps, we've gone to here.
Yeah, the fancy stuff is just constrained optimization.
So
The primal and dual stuff, I still struggle with, but the fancy stuff is.
Yeah, I mean, it seems like all it allows you to do is that you can just switch your the order of your terms and minimize instead of maximize. So so that's how you can translate between the two.
Yeah, I don't know if it's that simple. I would read about it a little bit before.
yeah, the key here is to get out you have to use the Karanj-Kuhn-Tucker and then you simplify to get to here. Where the final step is using the dual version. But a lot of the steps along the way are just beyond me. But I think
and it's also not clear where the KKT, where those constraints come from.
yeah, exactly. Yeah, I guess you'd have to read the original paper. So here's where we are. I think, and then basically all this is doing below it is we're going to represent this in some vector form. So we're going to say, really, we can rewrite this. We can rewrite this by saying, okay, we have some Lagrangian alpha transpose this matrix, which is the summation of yi to yj times x of I times x of j transpose, right? That's how we get this time. So it's this transpose that matrix times alpha plus, and then rewriting this in terms of the identity matrix in alpha. Mm-hmm. So when we write it as this, we're able to use a quadratic programming package to solve our optimization problem, so we can find the maximum margin, or really what it is the optimal, optimal margin classifier, right? We fudged it into the optimal margin classifier formulation for us to solve. Okay. Yeah, so this is, I think another important thing to point out, even if we can't necessarily follow the KKT condition, right? This is the complementary condition where it allows us to do some stuff. These points here where we make the constraint that the you know, smallest, the margin of the points closest to the classifier is going to be equal to 0. We consider these points are support vectors.
Oh, okay. So this makes sense.
Right, alpha I greater than 0. This is where x of I is a support vector. So these points labeled in red. And that is related to our, you can see how it's related to our Karush-Kuhn-Tucker condition, right? Because where g of x equals 0, alpha must be equal to, g of x is greater than 0, alpha equals 0. Where g of x is equal to 0, alpha is greater than 0. Okay. Okay, so let's move to here. So here's another, this is, we're approaching the end of this lecture. So again, we have our linear separable data. We've identified the support vectors, where these are the closest points to our classifier. And, we're defining our normalized margin with this, and we're finding, theta such that we've maximized the margin, where, at our support vectors, we had the constraint such that x of I times theta plus b is equal to 1 or negative 1, depending on which side of the classifier. So in this scenario, we're looking at linearly separable data, right? It's pretty obvious from here. But if we go down to this example, this is not obvious, right? If upon first glance, you look at this and you say, this is not linear separable. How can I draw a line that is going to separate out all this? You really have to draw a circle. One way to get around that is to map this onto something else. So what we're going to do instead is we're going to say, let's map it to a higher dimension. Let's square x of I and x squared. And so once we do that, I think it's a little more than that, but yeah, they minus some constant and then they square it. But now we have this, we've mapped it into this higher dimensional space, right? And now we can use a linear classifier. So if I annotate, right, I could do something like this. It's essentially a straight line, right? Mm-hmm. Whereas I couldn't use a linear classifier here. Now that I've mapped into this higher dimensional space, I can. So if we go down to here, so in X space, this is our optimal margin classifier equation that we derived earlier. And even though in X space, it's not going to work, right? Because we can't really come up with a linear classifier. But let's say that X is n by d, so it has d dimensions. And if we look at this term, we see that we have this inner product x of I times x of j transpose. And we know that that's going to end up being a matrix n by n, right? Even if you had millions of dimensions to x, so let's say d is literally 1 million, is that going to change the size x transpose x? X times x transpose?
No.
No, it's still going to be n by n. So, okay, so that's important to note, because what we could do is let's say that we take this x, we map it onto z, right? So we're in this higher dimensional space, and then we put it into our optimal marginal classifier. We can get the job done. Here are our support vectors in yellow, right? And all we're doing is we're using the same optimal margin classifier, just in higher dimensional space. Are we following?
Mm-hmm.
Okay, so we've mapped it. Now we use the classifier. It works. Here's our support vectors. But let's throw it back into X space. This is what it looks like, right? So we've used a linear classifier and we got the job done, even though at first glance, we had a non-linearly separable data set. All we had to do was map it into a higher dimension. And here are the support vectors that correspond with the ones in yellow. And so this is going to be the motivation for what we're going to do next is kernels. But really the takeaway here is we've seen data sets that are linear separable or not, right? If you can draw a straight line through it, it's linearly separable. If you can't, it's not. Perceptrons are one way to come up with a classifier that learns, that predicts as it learns, and you're going to end up with a linear classifier, but it's not perfect. And so one way that we can do a little better is by using these support vector machines. And we've seen the geometric intuition behind it. We've talked about two-dimensional space, but really, it works for higher order dimensions. And what we're seeing now is that it's actually, if we map first, then we can take really high dimensional space, or we can take really high dimensional stuff and get the job done with our linear classifier. Any questions here?
No, that example was pretty cool though.
Yeah, that's really good.
Do we know if if a data set is not linearly separable in a lower dimension, that will hold for all data sets? By raising it to higher dimensions, that we could still get separation?
Well, we'll talk about that more, because you might not be able to get separation in higher dimensions, and you can still, but you can still come up with a classifier. It just, what we're going to call hard classifiers, where we're going to assume it's completely separable, and it's either going to fall on one side of the line or the other, and there's no errors. But if you have noise in the data set, you can use soft classifiers, and that's going to be a little better.
Okay.
Kevin, any comments, questions?
You said me?
Mm-hmm.
No. I'm kind of in the same boat as you are, honestly. My mathematical intuition of this topic is kind of shaky, but I understand conceptually what's going on, which seems like you guys do now too.
Yeah. The cool thing about SVMs is that you don't have to learn the mathematical. Apparently, these are they call them a turnkey algorithm, because there's no parameters. You just push it out and it goes. You just need to pick. In this part, we're gonna learn about kernels, and depending on your application, maybe if you want to be like Kevin and you want to do machine learning algorithm that is particularly good for, I don't know, cancer, then you might redesign your kernel. But for the plebeians among us, fuck that. Slides. I'm sorry. So, if we're ready, I can move on to kernels.
Yeah.
Do you guys want me to switch the recording again? Okay.
Okay. So this is where we left off last time. We have this obviously linearly separable data set. Our support vectors are where our constraint is active. The x of I times theta plus b equals 1 or -1. And we define our margin, our normalized margin, using this. And so this is our geometric interpretation of what support vector machines are doing. But now what we're trying to do is, what happens if we don't have linearly separable data sets? This is kind of what Bam was asking. So if we have this really ugly, where you have to draw a circle, that's not linear. Or if you have noise in your data, I've got reds with my blues. How do I account for that? And the two ways we're going to do this are, first, we're going to use kernel trick to do stuff like this. Then we're going to talk about soft margin support vector machines to allow us to account for errors without overfitting. So here's the idea. Let's say we're basically taking some version of our circular reds and blues, but I guess we've inverted the colors for this. And you might ask yourself, okay, well, how can I use a linear classifier on this where I obviously need to draw a circle? And one way to do that might be to map it using polar coordinates. So in the last lecture, we mapped it by squaring our x's. In this one, we're going to map it using polar coordinates. So where we have the radius r, that's the distance from some arbitrary center we chose. And then we have some angle beta. So now we have r and beta, we've mapped it to polar. And once we do that, it's pretty clear, there's some r value where it separates. We have a linearly separable data set at this point. And so once we've mapped it, we have linearly separable. And then when we throw it back into the original space, it acts like a nonlinear classifier because it's a circle, right? So the mapping is really powerful. Here's another example. This gets back to closer to what we were doing last lecture, where we're going to throw it into some higher dimensional space. And this time, instead of just squaring it, we're going to do square, and then we're going to also do some root 2, x1, x2, right? So we've mapped it from 2-dimensional to 3-dimensional, right? So now we've taken this, it looks more like this now, which is really cool and pretty. We're going to make some hyperplane, this denoted by this blue box. And once we're able to do this linear hyperplane, that allows us to separate our reds from our blues. Because, I mean, it's the same thing. Here we did polar coordinates. Here we did higher dimensional Z space.
So cool.
Yeah, it's really tight.
So in this case, can you necessarily, I know you don't need to map it back because you can just look at each one of the points in the new coordinate system, like when you're testing new points, but can you map this one back or no?
I think you can.
Because it would just be the inverse of whatever the transformation matrix is, right?
I think you can always map it back to visualize what it's going to look like. I can't comment on the inverse of the transformation matrix.
Okay.
This is just the more generalized version. So we can think of the mapping with this phi. So we have phi, 5x is going to basically take, phi is going to take x as a parameter and then map it such that we go from D dimensions to big D dimensions, right? So we start with here where our data set is D dimensionality. We're going to use phi, this is the mapping function, where now we've put it into the big D dimensionality, and we're able to use our linear classifier f of x equals 0 in order to separate our data. So we're learning by doing this linear classifier. Also, I'm a little bit more shaky on this lecture than I was last one, so bear with me. I might stumble a bit more. But our mapping 5x, we're just gonna represent with z. So that's in the z space. So we're gonna say z times theta plus theta naught. It looks just like what we saw in the last lecture. Instead of, did Bayon disappear?
No, I'm here.
Okay.
I'm grabbing my charger.
Oh, my bad. Okay, but instead of x, it's z now, where z represents x that has been mapped to a different dimensional feature set. Are we clear on that?
Mm-hmm.
Okay, so that's just the notation. So what we're doing now is, this is the meat of the kernel trick, because what we did here is like we saw there's multiple ways to map this into a different dimensional space, or Z space, and still get the job done. And the kernel, all that's saying is like, we can generalize that mapping with our kernel. And it's powerful because if we look at this, we see that our Z space, Zi plus Zj transpose, is just the inner product, right? And if you remember from last lecture, the dimensionality of that doesn't change regardless of how many dimensions you choose, right? Big D can be infinite, but Z, our inner product, is still going to be n by n. So let's look at this. Yeah, I think all this is saying, based on my understanding of this math notation, we can still use we're still using our optimal margin classifier, and we can still use quadratic programming to solve for the theta that's going to get the job done. And then same result as hard SVM, solve our alphas using quadratic programming and predict a test point Z in Z space. I'm not sure how to interpret that, to be honest.
Yeah, I was just saying that we use the same quadratic program method, but now we're just solving for Z instead of X as we did before. Or now we're just using Z instead of X.
And
So like
yeah. Go ahead.
so like you have some test data point X, you map it into Z, and then you use your QP to find your alphas. And then the prediction will be, okay, do I have a positive value for that or do I have a negative value?
Okay. We're going to represent, okay. We're going to let Z times Z transpose equal our kernel X times, X prime, right? Given 2 points, X and X prime, we need the inner product, right? And we're going to say the kernel is going to give us that inner product of X and X prime. So for example, if we have X equals X of 1, X of 2, and we're going to do some, it has 2 dimensions, but now we're going to map it onto Z. All right, how many dimensions does Z have? This is actually not hypothetical.
Two, right?
No, so do you agree?
No, it's like 7, right? 1, 2, 3, 4, 5, 6, 7.
I'm pretty sure it's 7. I can
Wait, sorry, I zoned out for a second. You asked how many dimensions there are for the transformed
shit.
where are we?
This has 5. 1, 2.
Oh, X1, X2 are repeated.
Oh shit! I didn't even see that. Okay. Okay, this has 5 because we had to be careful looking at that.
Okay,
All right. Anyway, so right. So we're going to say that the kernel is equal to the mapped version Z prime times Z transpose. And both of these, because these are equivalent, these both equal this, right? The cool thing about the kernel, we can also calculate X and X, X prime and X, X prime and X prime. These would be similar outputs. So the trick is it possible to determine this value, right, which we determined is the same as this, which is the inner product for our optimization problem, right? Can we calculate, here we go, this kernel without transforming X and X prime, right? Because if we have like a lot of dimensions, in this example, we went from 2 to 5, that can be a lot of time, especially to calculate that inner product. So we have this data point 1 in X space. All right, cool. Data point 2 in X space. These are 3 dimensions. And then now we're putting it into Z space. All right, look, we've just really increased the dimensionality. We've mapped it. Data point 1 and 2 have 5 dimensions in Z space, and 1 is for the bias term. So that's the bias term here. We want to calculate the dot product for the kernel. So we have this, we've taken the X, X and X prime. We've mapped it onto our Z's here. And we're saying it's going to be equivalent to this statement, which is the Z prime times Z transpose. They've simplified here. So I went from here, simplified it. And what we can see is that this is actually equivalent to saying X prime times X transpose squared is the same kernel as if we were to map it and then do this calculation and set that equal to K. I'm not sure if I lost myself, so let me know if I lost you too. All right, is everyone following them?
I think so.
Mm-hmm.
The goal is to compute this kernel in less steps. We don't want to map first. Here's the mapping. and then do the inner product, all right, inner product. And it says what they're doing is they're proving that we can map it, do the inner product. This simplifies down to this. If we remember that x and x prime equal this, the kernel is really only equal to x times x prime times x transpose squared. They just proved that.
Oh, okay. So what this is doing is that you're before you even map over into the z into the z not plane, but you're basically you're proving that you can do it originally with x or x prime and x, right?
Yes.
First, and then using the equivalence, then move into the z.
Right. So we're getting the output we need to do our optimal marginal classifier optimization. We want this output, and instead of having to map it first, we want to use a kernel, and we're going to just take our original x prime and x transpose and get the output that we would have gotten from mapping.
Oh, okay.
Okay. So that was just an example of one kernel. I think, again, I'm tripping over these slides a little bit, but what we would find is that, let's see, x of rd and this goes to some z polynomial order q, the equivalent kernel is going to be this equation here. And it really doesn't matter what polynomial order the kernel is. It could be 2 or 1000. Remember, the inner product is still going to be n by n. We're going to get the same value. And what will happen if we have d equals 10 and q equals 100? We have to compute the inner product explicitly, right? So if we had d equals 10 and q equals 100, and we had to map it first, and then compute that, and then throw that back into our optimization, it's going to be a lot more time than if we were to just do this. Well,
yeah, it's relatively still it's relatively better.
I'm not sure if I'm saying this right, but let's move on. All right, I think I see what's happening here. So let me just let's abstract away from the slides a little bit. What Madi is trying to show us here is that we need to know, we need to have a kernel such that in some z space, the inner product is equal to if this is an inner product in some z space z, we have a good kernel, right? Our kernel is good if we can do some simple computation like this with the x and x prime without us having to map it into z and then throw it back as an inner product. That's the definition. So this function will take us to infinite dimensional z. Congratulations. I think all that means is that
it'd be ridiculously expensive to do it in z, and so this kernel's good because it's simple,
right,
with x and x prime.
Yeah. So here's an example of using the radio basis kernel. I think, yeah, so this is some kernel that exists in the same way that like different probability distributions exist. There are different kernels. So here's one, this is the radio basis kernel. And in action, we have this data set of blues and purples, and we have some slightly nonlinearly separable case, and it's going to draw through this pretty well.
That is so cool.
I think I'm still a little confused what's happening here. I'm not sure.
I think those are your like if that's your if the kernel's your decision boundary, is that showing? Is this next thing the darker black line showing you the potential margin? One of the margins. That's just my guess.
I think this is the original separation line,
Right. Yeah, that'd be the decision boundary.
but I think this is before we've trained anything. And now we're mapping it, we're trying to train a decision boundary using the radio basis kernel, and this is the output we get.
Oh, okay. Okay, that makes sense.
It's a little different than the original. And I think the point here, yeah, I wish Madi had landed the plane on kernels first. But I think for this takeaway is that, like, even though kernels allow us to generalize mapping into a higher dimension to use a linear classifier, sometimes we kind of overkill here, because if you look at this, it's like extra curvy, and usually that's a sign that decision boundary is super wiggly. That means it's probably overfitting, right? So even though the actual line is this green one, using the radial basis kernel, we've got this really wiggly black line. We don't want that, right? So the question Madi poses is, are we killing the generalization by going to infinite dimension and overfitting? And you can ask yourself the question, in this example, how many support vectors do we have?
Many.
Right, we have a lot of support vectors. So it's using all those outputs to create some decision boundary. And maybe it's best if they didn't. So I think this is trying to say that, actually I can't read this notation. Can someone else read this notation and put it?
I don't know what E out is, but expectation of E out, maybe error, is less than or equal to expectation of the number of support vectors divided by the number of data points minus 1.
Okay, so I think that's a fancy way of saying the error for the overfit is greater than the actual error.
Well, so if you, the expectation of the error is, the expectation of the error for the support vector is less than their mean. Oh, no, that's not their mean. That's the number.
But it's saying that it's the expectation of your error boundaries should be like the expectation or less than or equal to the expectation of, I guess the number of support vectors would be like the decision boundary lines. Like it signifies the like upper bound and the lower bound of the range, right? Mm-hmm. And so like if I have I don't know why it's dividing it by n minus 1.
Yeah, let's go. That important.
Okay. Why do we do this? All right. So basically, we had, if you remember from last lecture, we had this matrix, we had these inner products. We're going to replace that with our kernel value. Right? Because essentially what we're doing is allows us to map into Z space, use a linear classifier, get the job done. And it turns out that all right, so we want to ask ourselves if
oh, this man was pressed. He said, I don't care.
I just like, I mean, if you want, we can try and like think.
No.
I think the more, this is the question that kind of, I think whether or not support vectors, are turnkey or not, the question really is, or if you're going to use the kernel trick, the question is, how do we know a kernel is valid, right? And that's useful if you want to design your own kernel for whatever application. And so for any given kernel, we can check the validity by construction, math properties. I guess you just don't design your own kernel. I don't know. So it's going to be valid if it's symmetric. It shouldn't matter which order you're putting in your
data.
features, your data. I guess not your features, but your data points. And the matrix must be positive semi-definite. There's a proof for this. It's pretty complex, but this is Mercer's condition. So as long as this is what we call a kernel matrix. Well, this isn't actually the kernel matrix, but like if you were only to take the Ks and you take it for each data point, like the summation, the double summation of I's and J's for all your data points, and you throw them into the kernel. Let me just write that out. I think I actually do know the math for this. Fuck. Right, where I equals 1, is it to n? J equals 1 to n. And then this is basically k of x of I and x of j, right? That's going to give you your kernel matrix K.
Mm-hmm.
This must be positive semi-definite.
Yeah.
And then, like I mentioned, there's lots of different kernels. You might find yourself in a position where you're designing a kernel. You probably aren't. And so you could do the linear kernel, but the problem with this is that you don't take advantage of the kernel trick, because the kernel trick allows you to map it to higher dimension D and then get your output. You linearly classify using that. So like if you already have a linear separable data set, I guess you'd use a linear kernel, but if you want to map it to a higher dimension, D, you can use a polynomial kernel like this, which we kind of derived above. Or there's other kernels you can do that are so valid, they look a little different, such as the Gaussian kernel or the radial kernel that we saw before, where these are infinite dimensional feature space. Now this is getting to Bayan's question from last lecture, which is there's two ways that can be non-separable. Here's what we looked at before, which is this isn't necessarily linearly separable. We can use a kernel to map it into some other dimension space and get the job done. But here, like it's kind of linearly separable, but there's some errors. And so what might make sense is to use a soft support vector matrix. What that basically is saying is that instead of saying that, in this case, there's no violations. So we have our maximum margin and no values fall into the margins, right? But here we can basically allow for values to be inside of our margin. And we can do that by using the slack variable Greek C. Is this eta? How do we pronounce this?
I think it is eta. I think so.
I'm just going to refer to it as slack variable.
Okay.
So instead of like this hard where I think before we didn't have this term, right? So it was like this, where it must be greater than 1. But now it's like, well, it can be on the other side of our support vector. It doesn't really matter. It's fine. And what we'll do is we'll say the total violation is the summation of all the error. So when we optimize, we want to get some value. Well, I'm not exactly sure what that means. I'm going to keep going. Here it is.
For all the points, right? So this is for each individual point condition, is for each test point and each, well, I'm sorry, each training, this is all training, we're all in training. So each output for the training, yi, and futures xi, and then the total violation of yeah, basically the total slack is the slack added up for every single point, every single training point.
I see.
So hopefully most of them will be 0.
Right. Okay, there we go. That's a good way to put it. Okay, so I was like, but I think I got confused because here we have C, the hyperparameter, which we pick, but this is computed. So that helps. And basically what we're going to do is we're going to represent it using this new optimization. Again, this is I think this is still I don't know if this is the primal. Is this the primal? It doesn't matter. This is our optimization, our optimal.
No, you're right. It is the dual. It's the primal dual.
Okay, this is the primal one. And now we've introduced this total error, right, in this term, which is like basically the relative importance of the error, which we'll choose. And with this, by minimizing this, we're punishing our optimization for having errors too high, right? We're minimizing by including this in a minimization term, we're also trying to minimize the error. We can account for error, but we don't want that much. And we're also going to include it in our constraint. So this allows for each of these data points to, have some cushion against necessarily being a support vector M1. Mm-hmm. And so again, what we're going to do is here's the, when we use Lagrangian to try and, I guess, account for this inequality, we're going to do a similar step here, where now we've added the error term, and we're adding that into our constraint. And then now our Lagrangian is going to have another parameter, another term, and we've added that into here as well, plus this total error term. Madi is going to do a wonderful derivation, and we're going to prove to ourselves that that makes sense. All right, and so I guess now we have different types of support vectors here. This is, and look at this slide in great detail before I started lecturing, but we can see that before we had these support vectors that were, where this was equal to the margin value was constrained to be equal to 1. And we have some Lagrangian that is not 0, but less than C at this point, right? Where C is the relative weight that we picked. That's a hyperparameter we added. And then we have some error values that are inside this margin, this one, where our Lagrangian is just going to be equal to C. So we have our margin support vectors, where we have, I'm not sure what this beta, oh, okay, I guess beta is this difference between the Lagrangian and our relative, what's the word for this? The relative importance of the first or second term. Okay, so yeah. So we have our margin support vectors here. We have our non-margin support vectors here. I think that's the takeaway from the slide. Any violating points become support vectors. So anything that's on the wrong side is going to be a support vector. I don't think Andrew Ng went into detail in terms of how to choose your proper hyperparameter C. So I don't really know how this is going to work. But I guess there's a method called cross validation.
He knows too, hasn't been listening the last few lectures.
Yeah, we know cross-validation, bro.
I was listening to the past few vectors. Just jog my memory.
You just separate into you basically separate into testing and training, and then you run your method with a C, I guess in this case, or run your classification thing with some training data, with some C chosen, and then you like check that against the test data, and you compute the error, and you do that for different C's, and then you basically minimize the error that you get, and that's your cross-validation.
Also, just this very manual. I think the word they used was, I don't remember the word they used. Experimental.
Yeah, I guess.
You can use, and you keep guessing till it's right. Okay. So here's the summary. Classifiers can be learned for higher dimensional space without actually having to map it to higher dimensional space. That's what the purpose of the kernel is. And that allows for data to be linearly separable in higher dimensional space, but not in the original feature space. And kernels can be used for support vector machines because when we, put it into our optimal marginal classifier, we end up with the scalar products. They're not necessarily tied to support vector formalism. So one thing that Andrew Ng pointed out is that you can use the kernel trick for other learning methods. So you can use the kernel trick for principal component analysis and logistic regression as well. It's not necessarily tied to support vector machines, although they're commonly used in support vector machines.
Mm-hmm.
That's the end of the lecture. Are there any questions before we stop recording?